Hi, so this will be the second video for the release number 2 of the Machinist project. What we're going to do in this video is we'll go over how we implemented one of the major features for release number 2, which is deploying the simulator service on the Kubernetes cluster. Now, this might sound simple in theory, but actually there was a lot of configuration that we needed to do both on AWS as well as for our Kubernetes cluster. So what the feature is basically we've packaged up the simulator service in what they call a Helm chart. Helm is a tool for deploying services on Kubernetes. It lets you package up all these Kubernetes resources, which are described in YAML files. It lets you package them up in a single folder and deploy this service with all those resources collected together as if it was a single package. It's sort of like a package manager for Kubernetes. So what we've done is we've created a simulator chart. In the simulator chart, we have templates that are written in Go templating language. So with Go templates, we can actually insert values in our Kubernetes resource documents before we deploy them on the cluster. So for example, this is a deployment resource. The deployment resource specifies what pods need to run in the cluster. In Kubernetes, containers run inside of pods, and Kubernetes schedules these pods across the nodes in your cluster. In order to deploy a service, we have to make a deployment resource that tells Kubernetes how many pods we need to run, what resources each pod should have, and what container image it uses. That's the deployment resource. To expose our service from the cluster, we need to first create a service object. What the service object does is it binds to all the container endpoints that are spun up by Kubernetes. When Kubernetes schedules new pods to run on the cluster, it attaches them to this service object. The service object has its own name in the internal DNS system of the cluster. So what that means is that we can create, let's say, 3 replicas of the simulator service, so 3 containers running in the cluster, and we can bind them to a single DNS name. What that lets us do is other services in the cluster can refer to the simulator service through the DNS. They can access all the simulator APIs as if it was a service running on the internet. But really the DNS system is only internal to the cluster. So we've created a service object. Even after creating this object, we can't actually expose the service from the cluster. The service objects are only accessible from inside the cluster. So to allow users to actually access our service, we need to create an ingress resource. What an ingress represents in your cluster is basically a gateway to the outside world. What it does is it specifies routing rules where, given a specific host name such as api.flapflap.io, we can tell Kubernetes where this host should be routed to in terms of the service name. So like we described, we created a simulator service which load balances traffic across multiple pods with multiple pods that are running our container. And we've created this ingress resource to expose it from the cluster. But even when we create an ingress resource, how does Kubernetes actually perform this routing? Well, Kubernetes itself can't do the routing, can't fulfill these routing rules. What we need to do is actually deploy an ingress controller on the cluster. The ingress controller is basically just a web server which acts as a reverse proxy and fulfills all the ingress rules that are created in the cluster. The ingress that we're using is called Ingress Nginx. If you've deployed other kinds of web apps, you may have used Nginx as a reverse proxy. What Nginx can do is it can sit in front of your app and it can cache requests, it can do load balancing, and it can host multiple virtual servers. So basically the ingress controller is just a reverse proxy. To create the ingress controller, we have to create a lot of different resources on the cluster. What these things are roles, their config maps, service accounts for the ingress controller to use in order to access different resources on the cluster, and various other Kubernetes resources. So after creating and configuring our ingress, we can then create ingress resources and have them fulfilled by the ingress controller. But that's not the end of the story. The ingress controller actually is not the gateway to our app. Really, there's another component that's sitting in front of the ingress, and that's the load balancer. So on Amazon, when you make a request to api.flapflap.io, you won't hit our ingress controller. What you'll hit is a network load balancer inside our VPC on Amazon. The network load balancer has been configured such that it routes traffic to the nodes that are running the ingress controller. So how it works is our cluster is composed of a bunch of virtual machines as well as some containers that are running directly on a service called AWS Fargate. So that's our cluster. The ingress controller is running on the master nodes of our Kubernetes cluster, which are actual virtual machines on EC2. The network load balancer gives us a static IP address that we can use in our DNS. We can make a DNS record for api.flapflap.io that points to our network load balancer. When we receive traffic at the network load balancer, that gets forwarded to the master nodes that are running the ingress controller. And then the ingress controller, having read the ingress rules that we've created on the cluster, does the routing and the proxying and the caching and whatever it needs to do in order to fulfill this ingress. The other thing that we do at the ingress controller is we terminate TLS. So the actual SSL certificate is being served by Nginx, not by the simulator service. Not only that, but TLS is routed all the way through the network load balancer into the cluster. Where we terminate TLS is at Nginx, and we configure TLS directly on the ingress resource. The thing is, how do we actually get this SSL certificate? That's another component that we have to configure on the cluster. What that component is called Cert Manager. So we actually have a folder here for our Cert Manager config and all the IAM policies that we needed to create on Amazon in order to configure this service. So what Cert Manager does is it communicates with Let's Encrypt, which is where we're getting our SSL certificates, communicates with Let's Encrypt and with AWS Route 53, the DNS server, the DNS system that we're using for flapflap.io, communicates with those two services to fulfill the so-called Acme DNS 01 challenge. What this challenge is something that's designed by Let's Encrypt. When you want to provision a certificate from Let's Encrypt, you need to complete a challenge that proves that you own the domain that you're requesting a certificate for. We've opted to deploy Cert Manager and have it automatically fulfill these requests whenever we create ingress resources. So actually, we didn't have to do any extra config to create this SSL certificate other than listing it over here in the ingress resource. By listing it in the ingress resource and having deployed Cert Manager, properly configured with the IAM policies, with the service accounts, and the IAM role that it needs to assume in order to change records on Route 53, what that does is it allows Cert Manager to complete these DNS 01 Acme challenges for Let's Encrypt. When it completes a DNS 01 challenge, Let's Encrypt provides the certificate to Cert Manager, and Cert Manager is going to install that certificate in the Kubernetes secret specified in the ingress. So we've basically set up an entirely automated system for provisioning SSL certificates. And the best part is we can use this same exact service, Cert Manager, in order to provision certificates for any other ingress resources that we end up deploying on the cluster. For example, if we end up making a new subdomain on the cluster, or if we need an SSL certificate for Machinist flatflop.io, let's say that we choose to deploy the front end also in the cluster, we could have those certificates provisioned automatically by Cert Manager. It also handles renewing these certificates, because the one thing about Let's Encrypt, even though certificates are free, they only last 90 days. So that's a lot of discussion about Kubernetes related things, and all of this actually took a lot of work to set up. But the thing is that this is just DevOps work, and it doesn't actually fulfill any features for the user. So one thing to keep in mind is, now that we have this infrastructure in place and we have CI/CD pipelines that deploy on this infrastructure, we can then create more services that we need to implement features for the user. So this is getting pretty long, this video, so I'll end it here. That was one of the major features we did in release number 2, is the DevOps on Kubernetes. Thanks for watching.